Yeah, so I changed the title a little bit. The previous one is a little bit ad hoc. So we changed the title to World Model for Representation, Generation, and Robotics. My name is Yanzhi Wang, currently professor at the Northeastern University, also associate director of the Pear Center, and also co-founder and chief scientist of the Embodied X, which is working on the robotics. So our goal is towards the open source world model in the academia. And then we, at Northeastern, we have defined some sort of definition of world model, including the following 4 criterions. None of them, the current world model actually meet all of them, including the world model that we developed, but that is fine. At least we want to go toward this goal. So we want to sense and learn the real world knowledge. We need to predict and generate the real world scenes. We want to reason and control according to the physical laws. And also we need to act robustly with a human in the loop. So currently there are many groups working on the world model, but then there is even no clear definition. And also there is no open source and physically grounded world model from the academia. And although the world model can have many applications, for example, like the disaster prevention, networking, smart manufacturing, and robotics. So we want to, when we evaluate a world model, when we work on a world model, we also need to think of how it can be generalized, how it can be mapped to the real problems. And then we see that which one has a better potential. So there has been multiple categories of the world model, including the first one is 3D, mostly focusing on the 3D scene generation, but this has nothing to do with the temporal or physical laws. One of the examples is World Labs, and also there are many of the 3D generation works. The second one is a JEPA-like representation learning and the prediction. This is mostly predicting the next speed, the next step. This can be integrated with the physical laws, but this is essentially a small model and nothing to do with generation. So mostly we have evaluated on the robotics and found that because the model is a little bit small, it can be generalized to robotics or smart manufacturing, but only on simple tasks. So the thing that we found that is can actually have more potential or actually representing and generating the word. It can use encoders, LLMs to generate the word for next state prediction, for physical law representation, and then we have a generation. So then this is category 3 and category 4, which is the controlled real-world scene generation, and also the human interactive scene generation. So both has a representation and encoding and a generation. So they are essentially similar structures. Encoders, multimodal encoders, including video and also text, and also a generation. So it's just one focusing on more of the physical prompt and also the relationship, another one focusing on human intersection. So we start from some of the representative ones, like the NVIDIA Cosmos, which is a recent building. So for the applications, I think one of the very key application is embodied AI and also the manufacturing. This also matches with actually the industrial and actually the needs. So this will be a key application of the world model. This is the thing that I focus on. And this is because the world model can help with the control with the human interaction, planning, data generation, and 3D reconstruction. So we hopefully that we can have one world model with some fine-tuned LoRa structures, and we can satisfy all the needs with the smart manufacturing and embodied AI actually for, throughout this process. So this is our goal. Yeah, so our starting point is NVIDIA Cosmos. This structure is shown here. So it's generally encodes a video, it encodes a prompt, and then it has a cross attention and it's trying to generate the scene. So it's somewhat considered to be state of art, but this actually has some major limitations, as we can see from here. So we can see that it's not exactly physics aware, and then the representation is sometimes the object from nowhere. So we found that the problem is that the video encoder is quite weak, and it actually cannot be used for reconstruction. So we need to change this video encoder. And also the generation is really short term. It's only 5 seconds to 10 seconds. Recently, there has been many work in long-term generation, but they typically work on very small model. So in terms of the Cosmos, especially the large Cosmos scale models, there has been limited work. And also there is, so the physics awareness is also limited. So the physics awareness is mostly through the inherent physics scene training. It means that the training data is physics aware. It's auto-driving or robotics. But actually there is no explicit laws or requirement or enforcement of the physical laws. So we want to mitigate all these shortcomings. So we can see that currently, as a Newton cradle as an example, as also in the Sarah has just shown, I mean, so it's generally quite difficult because they are actually not physics aware. But actually, these are two different things. So if we see from these three videos, we can see that there are both mistakes, but these mistakes are different. From those kind of Sora or Google Wheel, the mistake is they can generate a Newton cradle, but they don't know how it operates. So the generation of the video encoding is okay. But from the NVIDIA Cosmos, its video encoding is very weak, such that they don't know what is Newton cradle. But the operation is more physics aware, although it just does not actually do the encoding. So this is actually the limitation here. I mean, they are good. I mean, both have limitations, but their limitations are somewhat different. Okay. So because NVIDIA Cosmos is open source, so we start from the NVIDIA Cosmos, and then we first modify the encoder, and then we make it text video to video. We exchange into a text encoder, a image encoder, but we make it video. And then this is our word base. And then from the word base, we do some continuity training, and we have benchmarking of the physics benchmarking. And then with this kind of improvements, we come into our second generation, which is the word gen. And then we apply for the robot. This will be the word robot. And also, we have many of the follow-up optimizations like voice and multimodality, like long horizontal controlling, and also robustness and reliability. So this is our flow of our work. So first, we start from Cosmos, and then we modify the encoder, and then train the encoder. So this is our structure. So this is our structure of the model, and then we change it to a Y encoder. And then this encoder is currently the best encoder from the image to video, and then we are going to train it to the video to video. So we can see that we have also optimized other parts, and including the video and VLM for prompt generation, and also the speech to text and chain of thought for the planning, and also the text to speech. So we skip the very much details, but then it's like the train with the video continuation data sets. We have our specific data sets that we have accumulated, and then we have done the pre-processing. So then we mask the first frames, and in this stage, we train the encoder. We optimize the encoder. And we can see that as long as we have done using the physics awareness data set, we didn't have explicit requirement of the physics awareness, but we can see that it's still okay. For 10-second, 20-second generation, we can generate physics aware videos. So this is, and already we can generate this and represent using our model. And when we compare with NVIDIA Cosmos, we can see that NVIDIA Cosmos generation, this is fully generation and from the same starting image. It's not very realistic because it generally comes from nowhere. And our base, this is only our base model, is more realistic. And also it's more long time generation because we train using the longer videos. So the generation will be longer compared with NVIDIA Cosmos. And if you have a real scene using the Northeastern University, and we can see that, so the problem is of NVIDIA Cosmos is that the people just come from nowhere, the cars come from and disappears nowhere. And actually we can see that our result is more realistic. And then this is actually, we can simulate the words better. So the limitation of the word base. So it's only word base. So there is still some limitations, including the limitation of the long horizontal generation. For example, if we really want to generate for a longer time, you will see that there is a color shift. And also there will be a speed change. This is very typical for the current video generation. But it's just we want to generate according to the physical laws. And then actually we can see that actually the speed becomes faster because after some time it forgets. And also there has some still limitations in physics awareness because we are implicit. We are trained using the physics video, but we are not explicitly to improve for the physics awareness. So we need to define what physics aware is first. Okay, so from the word base to word gen, we have two improvements. One is we need to train for continuity. Previously, we have trained the encoder. But if we don't touch the cross attention and the diffusion transformer, then there is nothing to do. I mean, there is still limitation. What can we do is the encoder is already done, but we need to train the other part. And also, we need to actually have a benchmarking. We will explain why. So we have our data pipeline that we need to collect the actual data because there is limited video continuity data. So we cannot rely on the public available data. We need to do the data processing. And then because many of the, even if we are using the real world data from the YouTube, I mean, the data is still in the clips. The data is still not continuous. So we need to use the AI coding for the continuing data generations. And then after this, we do a data filtering, and then we train the diffusion transformers using our training methods. So this is a categories of the data we have collected. This is a big amount of data. So including the auto driving, including the data from robotics, and also the general. So this not only includes the data released by the NVIDIA Cosmos, but also has all the data we have collected in the YouTube and other sources that we have compiled into all the data. And actually, for the filtering and cutting or pre-processing of the data, we have used multiple GPUs to do this. And then we filter out these movements, and then using the two large VLMs to double check, such that we are going to train using the physics grounded data, and also the data is continuous. So after doing this, we only trained at this moment using 20% to 30% of the data. And then we trained using the flow matching by freezing the diffusion transformer, by training the diffusion transformer and freezing the other parts. Because the encoder is already done, the encoder is difficult to make it more continuous. Yeah, but this one with careful data screening, I think we already got some good results. So before showing the results, we show the other parts, which is improving the physics awareness. So we are going to have our benchmarking. Because we have found some of the current benchmarkings, and then we found that it doesn't actually work. So those two benchmarkings are mostly from the AI society, but then they mostly train an small AI model. And this AI model is too small, such that it gives very misleading results. The correlation with the human evaluation is less than 30%. So because the model is too small. On the other hand, the physics society is evaluating by creating prompts and asking the large models, for example, like Google Gemini or the ChatGPT, and to give the answer to say that whether it's according to or violates some physical laws. But anyway, this still requires a large model. So this is the reason that we need to do the benchmarking first. We need to give scores. We need to have a model that input the video, we provide scores. And then we implement a reinforcement learning technique. This reinforcement learning technique, you can use a DPO, or you can use some more advanced reinforcement learning framework that extract the prompt and compare with the actual video and the generated video, and then with the scoring from our physics benchmarking, and then we improve the generation. So this is actually our physics awareness training. Yeah, so we discussed a little bit for the workbench that we done for the benchmarking, because as we said, the current benchmarking work is limited, either a small model or relies on the large model without tuning. We will show that using a large model is also not the best methods. So we start from the video generation, the data generation. We generate the prompt to that explains the physics phenomenon that describe the physics process, and then generate the video. And we generate the matrix, which is a comprehensive matrix from the computer vision perspective, from the Newtonian physics perspective, and also to the optics, to the materials, chemical, energy, and all of that. And we have a benchmarking agent. This benchmarking agent is a combination of the large VRM for grading improvements and also human evaluation. So it's an integrated method here. And finally, we are going to train our open source VRM evaluator, which will be open source in about 1 month. So this will be our VRM evaluator. We need to train a large VRM. And this VRM needs to be in the size of 27B, which is recently at the Quinn 3.5 model. Yeah, because if we use a very small model, it's very difficult to evaluate that the physics, actually the physics phenomenon. So this is our prompt collection. So we collected about 500 prompts, and then this is describing the physics process precisely. And also we use filtering, and also we use the AI method web coding for the further enhancement. And we have generated 3,000 videos using a number of methods, including our model at this moment, and also the representative world model generation. So this is a prompt collection, and we can see that it covers all of them, including the collision, gravity, momentum, flow, inertia, and also the reflection and the drifting, and it's a quite complete benchmarking. So this is a prompt and phenomenal generation. And then we need to consider the metrics and the grading as well. So the metrics including 2 parts. One of them is a video-related metrics, which includes, this is actually the video quality. And we learned this from the previous work on the AI-driven video benchmarking. And this, we can see that this includes the order, this includes the temporal, and the frame width and error, and also the plausibility, this kind of thing. So this is both subjective and also objective. And for our other metrics, so we learn from the physics related work, and we further expand to be much more comprehensive, including both mechanics, and also the others like optics, fluids, thermodynamics, and also chemical and energy related. So we are going to generate these questions or criteria. Instead of directly saying that does it comply with the laws of physics, but we convert into the questionnaires that the VRM can observe. But even if our questions are detailed like this, the VRM still cannot work by its own. We use 3 leading VRM models, including the Gemini, including the recent GPT, and also the Quinn 3.5 mixture of experts. Why we need 3? Because we need these 3 to mutually grading. They need to have the reasoning, give the reasoning of the grading, why it, according to physical law, under what second is wireless, and what's the reason. And we need to have the mutual grading and mistake correction. And also we have the selected human evaluation that actually evaluated, and we found much more correlation with with our agent. And also we train our open source evaluator. So for example, why we need 3? Because we found that Gemini fundamentally misperceives the video dynamics. This is actually the agent that we had developed for the grading. Actually, this one will be open source, and then to the community for the grading and for the evaluation. So this is actually open, and then we can see that these videos are actually from the YouTube. When we say that this is the water flowing, actually the Gemini give no reason. It says that there's no dynamics, so it is not correct. So for the dynamics, and then we are going to blacklist the Gemini. So, and then the next thing is, so for the Gemini, we have blacklist the laws, and then so generally for those, we cannot rely on the Gemini. We need to rely on the others. Yeah, but we cannot only rely on Quinn or GPT as well, because they have their blind points. For example, when the collision pass through, and then the Quinn will not detect. Yeah, and also GPT has its blind point as well. So we need to select and mutually correct them such that we make an overall evaluation. Yeah. So yeah, then we compare our word gen with our word base. So this is a word base, and then we can see that there is still some limitation because there is a color shift and then the speed change. But actually from our word continue or word gen, actually we can see that there is consistent color and speed and anything. And also we can see that this is our word base. And we can see that, I mean, this is, there has been a question about the seed dance. Actually, seed dance is a little bit different. This is open, this is closed source. In terms of quality, our word base is similar to seed dance. And and we are more physics aware. But the unique advantage of seed dance is that is integrated sound. This is very unique. This is great for seed dance. Yeah, but they are closed source. So we are going to make it open source. So we can see that our word base still have some color shifting and some blurs and then some problem, but then our word continue will be much better consistency. You can see that this kind of physics aware, or this is already better than Cdance. I'm not saying that the overall generation quality, but at least for the punch and then this kind of physics awareness, I think that is already okay. Yeah, and then another thing is about the to apply for the robots. So currently the difficult simulation is the dextral hands. And also how it according to the physical laws. So we can clearly see that this is very, very difficult at this moment. And we can see that even our word base cannot do it. One thing is a color shift, but this is a minor thing. But we can see that the second move, so see the second move, is still not very according to the physical laws because it's still not grasped very tightly and then it moves. But we can see that our work continue, we can actually simulate the force more better, and then we can to make it run smoothly, and actually we can somewhat simulate the force, and then we can have more explicit thing. So this we can simulate and actually control a dextral hand, which can have a better potential. So we can apply it for the robot, and then this is the next time goal. So we think that this world model can be integrated with robotics and embodied AI from almost all aspects, and this is together with embodied AI, the embodied X. So the world model can be actually the brain of the robot. So currently, the robot can act, can react, can do the exercise. They have the cerebellum, but actually they don't have the brain. So some robot companies like Unitree already can react, but then it doesn't have planning. We are going to add the brain to these robots. So the world model can help with the high-level planning, like the task management, task decomposition, just using a single model. It can use the action level, like for navigation, it can call the slime, or it can do the navigation, and also it can do the manipulations, even the dextral hands. And the world model can even also do the 3D reconstruction and scene understanding. So for the slime, we do not need to have the manual labeling. The world model can do the labeling. And then we do not need to go everywhere. We can take some pictures and then do the 3D reconstruction, so we can have the whole navigation of the robot. So this can be done using a same world model. So this is the reason that we can call it as a world model. And also we can have interaction of the human in the loop. So we're building towards this goal. We have not finished yet, but we're building towards this goal. So this is a world model that we're currently building. And based on our model, and then we are incorporating the voice constructions, we're incorporating the depth sensors, and then we are trying to use the model to do both navigation control and planning and reconstruction, and then so everything integrated with a model and we want to make it real time. So besides this, we also want to actually deploy. We don't want to use the H100 to implement the world model. If we want to actually control the robot, it needs to be implemented in the robot, or at least in the factory. So it requires lightweight implementation methods or more efficient or real-time implementations. So this is our work of the world deploy that we call the OmniX framework, that we do not need to rely on a certain hardware. We do not need to rely on CUDA. We generate everything in the basics of C, C++, or Rust. We don't use Python. So this is an extension of the GGML, which is a Llama CPP, but that one mostly working for the large language models. So we extended significantly towards image generation, towards the world model, video generation, VRM, VRA, speech recognition,
text-to-speech, all aspects of all models. And we can map it to almost all hardware, not only NVIDIA, but also AMD, also Mac and Snapdragon and those devices. So currently, sadly, actually, Sora is gone. So because it doesn't make profits, it's very heavy. But actually, we can enable, everyone can implement the next generation Sora, which can be the one, which can be LTX, which can be Cosmos or our model, totally free, just using their laptop and desktop. And we can generate a video just using our laptop, Mac laptop, in a couple of minutes. And we have just tested on that. So this will be totally free to use and open source. So when we get rid of Python, and then there is a lot of advantage. And then we can generate, because we have our framework and agent, so we can generate using the web coding to map any method into the corresponding implementation codes. Yeah, and this is totally automatic. Yeah, so and then we can see that there is clearly advantage among the hardware device in the memory accuracy in terms of quantization. You can clearly see that in terms of quantization, because the GGML has a very flexible quantization, so the accuracy is much higher. And also in terms of the speed, in terms of memory, obviously there is advantage because we do not need to have the memory, to have the libraries in Python. Okay, so we have the actual deployments. This is the deployment in the company. So the world model can actually control the robots. This is the left, and the right one actually shows the autonomous navigation. And then we're using the world model for the labeling and navigation as well. And also, this is in the Vineyard in the New York State. Yeah, so this is together with Embodied X. Yeah, thank you. And then, so yeah, we are open source these projects. And so, yeah, so if you're interested, then please take a look. Thank you.